So I remember doing these little car talks, the Young Students Encyclopedia, and going back over books after having dealt with the theory and after experiencing how people treat new ideas, how slow good ideas come into being, how nasty people can be. It's definitely, it gives me a richer understanding of how things actually work. And I'm fully convinced that this understanding isn't going to be accepted until long after I'm dead and gone. But that being said, it doesn't mean I can't share some ideas here. Sir Frank Whittle, born 1907 and 1990, and he died in 1996. I wrote it in there because this book is kind of dated. But see below, Whittle Wright. He's the one with the glasses on. Let's see if I can do it. Yeah, right there, right in the bottom. Says here, the development of the turbojet engine by young British test pilot and aeronautics engineer Frank Whittle revolutionized every aspect of the aeronautics industry, from the military aircraft and guided missiles to passenger airlines and helicopters. By dispensing with the piston crankshaft propeller system, the jet aircraft could be driven by a much smaller, lighter engine. Its tremendous power also paved the way for travel at supersonic speed. The principle in which a jet engine operates was first stated by the British physicist Sir Isaac Newton in 1687. To every action, there is an equal and opposite reaction. In the case of the jet, as the fuel is burnt, so hot gases are expelled. The reaction to this is a thrust which drives the engine forward. And basically, but the compressor, which is the vaned wheels inside of the inside of the jet, and they compress air, which superheats, and they put fuel in it, and it creates a huge explosion when the fuel mixes with the oxygen in the air. And then it obviously compresses it and then ejects it out the back of the jet at really, really fast speeds, velocities. And the reason why I wanted to discuss this specifically was that it's a good idea to understand that when you have chemical reactions that produce a lot of heat, you can produce a lot of thrust in certain directions, and things can be aligned in certain directions given certain properties of the star's interior. And I thought, wow, looking at Jupiter and its huge atmosphere, it isn't just a series of the sun heating it up and things just swirling around because of the heat of the sun. There are chemical reactions taking place. There are a lot of condensation reactions taking place that are taking gases and making them into solids and liquids. And the heat from those reactions has to go somewhere. And that's probably what drives a lot of the convective motion inside of Jupiter, inside of Neptune, inside of Uranus. I know Neptune has upper atmosphere windstorms that reach in excess of 1,000 miles an hour, I believe, or it might be 1,000 kilometers an hour, I'm not sure, but really, really powerful storms, far more powerful than Earth's hurricanes. And that's something that I was really thinking about a lot of, especially when in terms of the space shuttle. I remember watching the space shuttle go up as a kid, where you have the liquid oxygen and liquid hydrogen combining together, and those create water. And I was like, so not the boosters, but the actual RS-25 engines, those create water. It's like, wow, I mean, when the space shuttle went up, a lot of that was just is making clouds. And I thought that was really cool when I found out as a kid. I thought it was like car exhaust, pure and simply. And I was just, what? Why don't cars do that? It's like, if a space shuttle can do it, and I was like, you don't want to put rockets on a car. Be a bit dangerous. But that being said, the amount of hydrogen and oxygen inside of young stars is incredible. The three main elements inside the sun are hydrogen, oxygen, and helium. And the helium is obviously a non-responsive element, pretty inert. It doesn't really combine all that much unless it gets sucked in and pressurized, and then it can get trapped when the natural gas forms in later stages of evolution. But all that hydrogen and oxygen, when it's really hot and ionized like that, it's going to combine together to make water. And that heat has to go somewhere. So every time I look at the astronomers and they go, we don't know why Jupiter is so hot. We don't know why Neptune's so hot. We don't know why Uranus is so hot. It's because there's chemical reactions taking place inside of them, which are really, really hot, and they're causing a lot of the turbulent motion inside the star as it evolves. But that being said, that dog's barking a whole heck of a lot. But yeah, I just wanted to relay that, like, to take something such as an engineering project involving turbojets and turbofans and that kind of thing, and applying them to star evolution, you know, the mixing of the fuel to burn to create motion. It's a really valuable understanding to have. Just to look at stars as being giant chemical factories, if you will. That's, I think, the way forward. All right, I just wanted to talk about this book a little bit. I've been reading it again with a new perspective on life and how ideas sort of make their way into the human consciousness. All right, later, y'all.